Right.
Yep.
So thank you everyone for coming. This week, Richard will tell us about shape invariant for toric domains.
Thank you. And thank you again for the invitation. It's great to be here. Right. So this is ongoing work. Kerman. Zhang. Right. So I want to talk about some quantitative estimates on embedded Lagrangian tori. Right. So general motivation for these kinds of questions, I think, is just the embedding problem in symplectic geometry. So I'll just fix some notation for this. Right. So most of the time, I'm just going to work in R4, or sometimes identify with C2, and just a standard symplectic form using x, y coordinates. All right, and then we'll write, so for a symplectic embedding, let's use an arrow there, and so we'll write x embeds into y if there exists I really want to stick to Hamiltonian diffeomorphisms, right? So if there exists phi, it's the Hamiltonian diffeomorphism of R4 or C2 with phi of x. Right, so anyway, to simplify things, I don't really want to think about boundary or non-compactness or any of this thing. So if in doubt, really what I mean is for all k, right, so for all k in X compact, so in other words, you can embed arbitrarily large compact sets. Right, that's dimension 4, and then higher dimensions is harder, but there's some problem we can make some progress on. So I'll write S, this is S for a stabilized embedding, if X times C n embeds into Y times C n. So if you have a symplectic embedding, you get a stabilized embedding by multiplying by the identity, but it turns out a symplectic embedding isn't a necessary condition for a stabilized one. Okay, right, so we'll come back to that. So I want to focus on Lagrangian tori and examples of these, or the product Lagrangian tori. So LRS. So it's a subset of C2, I write it pi Z1 squared R Q squared. C2. Right, so that's a Lagrangian torus. So for all we know, this is a complete list. Okay, right. So this is a complete list of embedded Lagrangian tori in C2 up to Hamiltonian isotopy with one. Well, there's a one parameter family of exceptions, the Chekhanov torus, which I'm not really going to talk about too much. So, okay, so ignoring this sort of specific monotone example, we think of these as the Lagrangian tori in C2 up to Hamiltonian isotopy. Because there's no other examples. And they're all different apart from reversing factors. Okay, so we're going to study these. Right, and then what I'm going to focus on is the shape. Right, so given, right, so if we have a subset, so define, so for now we'll define the shape. That's H of X. Right, it's pairs RS such that, well, I mean, because of this reversing factor thing, we're going to assume that R is less than S and the product Lagrangian torus embeds into X. So in other words, there's a Hamiltonian diffeomorphism taking the torus into X. Right. So this is a subset of R2 less than that. Right, so it's a subset of the set of R less than S. So in other words, so this is the the Hamiltonian isotopy type of Lagrangian tori inside X. So it's the Hamiltonian isotopy classes of Lagrangian tori inside X. Okay, so this, we're calling this the shape. So I think the word shape goes back to Eli Ashberg. Well, I think he was the first one to use the word shape, but he used it for something slightly different. So, Eli Ashberg's definition was more general, but he was only kind of keeping track of area classes of the tori. Right, so we're, in principle, there's slightly more information here. We're keeping track of the Hamiltonian isotopy class of the torus. So these tori are all distinct of the Hamiltonian isotopy, but there are different tori where they're, if you pull back a Liouville form from C2, you get the same cohomology class on the torus, up to diffeomorphism of the torus. So anyway, so this is what we'll look. So we're going to try and study the shape. Right, okay, and then there's some formal properties of that. Right, well, okay. Well, if you scale the domain, C times X, well, maybe you should put a square root. I want to scale it so it's diffeomorphic to the symplectic form scaled by C. So this is equal to C times the shape. And this is a subset of R squared. You just scale it. Multiply all vectors by C. All right. If you have a symplectic embedding, well, right, so there's a Hamiltonian diffeomorphism taking X into Y, that implies the shape of X to shape Y. So this, so this is why I was saying. So you can, based on this, you can think of this is sort of some kind of symplectic capacity. In other words, it scales under scaling the symplectic form and it's monotonic under embeddings in some sense. And some capacities I think are supposed to be real value. This is like a sec valued. Sec valued, I think is really what I said. Sec valued. Right, so what else? If you take the shape of an intersection, so this is all almost nothing to prove, right? So if there's a Hamiltonian diffeomorphism taking a Lagrangian into X, you just compose, get it into Y. Right, so the shape of an intersection is contained in the intersection of the shapes. Right, and then for unions, think goes the other way, right? So the shape of a union contains the union. Okay. Right, so that's that. Right, so that's the shape. So now, right. So now we want to try to.
So you said, is any Lagrangian torus in C2 isotopic to one of these?
I don't know.
Or,
right. I think that's well. First of all, the answer is no because it's the Chekhanov torus. So there's a particular monotone torus which is not one of these, okay. But that's the only known one that's not. Okay. So you could conjecture that all the others are exactly one of these up to reversing the factors.
So is supremum over R plus S some kind of capacity?
Supremum.
You have a function from shape X to supremum R plus S.
But these things typically unbounded, actually, so probably not. You can look at like the minimum. Well, it's sort of related. Sort of the minimum of RS is maybe a more famous thing. But maybe we'll compare to that later on. But Right, well, okay, right, yeah, so, right, so let's see what these things look like. Right, so, okay, right, so calculations of these things. Calculations. Well, the only, right, so to do calculations here, I have to stick to what's called toric domains. So toric, so what does that mean? So there's a moment map, right? So define some notation I have, moment map from C2 to R squared, right? C1, C2. C1 squared. And then we say that X in C2 is toric. Right, so if X, sometimes write it X omega is the pullback of some subset under the moment map. So omega. So in other words, it's invariant under the standard torus action on C2. Okay. Okay, all right, so to write down a toric domain, I just have to write down a subset of R2. It's easy to do. All right, so for examples, well, I'll just draw them. All right, so it's, all right, so if you draw a right angle triangle here, it goes between C on the two axes. So I'm just gonna, all right, have an idea. Right, so I'm gonna label these things by lowercase letters. So we'll say BC is this subset here. The other one. All right, so this is lowercase EAB. So it's another right angle triangle, and then you can do a rectangle. Right. Okay. Right. So then we can define right. So what's called a ball of capacity C. So BC. Right. That's the domain associated to this. See. And then also you get an ellipsoid. And polydiscs also. So polydiscs. Okay. Right. So I'm always going to write the factors in order. So right, just sometimes the notation changes if you put one factor. All right. So these are examples of lots of others. All right. So these are examples of toric domains. Right. So okay. So what is the shape of a toric domain? Well, all right, so what we see, if you take a point inside omega, then its pre-image is a product Lagrangian torus inside X omega. So every point inside the moment image corresponds to an element of the shape. So a bit more precise, if you take all pairs RS such that it's supposed to be a subset of, maybe let's call this omega plus. Omega plus, by definition, it's a set of pairs, right? So I want this to be a subset of the shape, so I want R to be less than S. And then either RS is in omega or SR in omega. That is a subset of the shape X omega. So, well, roughly speaking, the moment image is automatically a subset of the shape, up to reversing factors. Right, but it turns out the converse is never true. Let's any examples. Right, so then let's define one more toric domain here. Just define. Right, it's going to depend on some parameter c here. So we're going to go 2c. Got 2c here, c, and draw this. So this is another subset of R2. Let's call this little q c. Capital QC. Right, this is the toric domain associated to this. Right, so then there's a lemma. Right, so this is related to your question, right? So for all R less than or equal to S, LRS embeds into Q R. Okay. So that's right, so the corollary here, so the corollary is that so inside the shape, you're going to get omega plus, but you're also going to get right. Okay, so you're also going to get some strip going up the y-axis. This content shape. Right, so what's M here? So M is the supremum of set of C such that QC. Okay. Right, because same here. Right, so if you take a point inside right, okay, well, right. So if QC is contained in omega, that means get this right here. Right. Well, right, if QC is contained in omega, that means all Lagrangian tori with R less than C embed inside X omega. So this, right, so this gives you this, right, and of course, this is an unbounded set. So if R is less than M, that means LRS is going to embed in QR, right? But Q, right, but since R is less than M, QR is contained in omega. Right. Okay. So this is an explicit construction of Lagrangian embeddings, kind of like wrapping the Lagrangian around itself. You can kind of kill the longest factor. Right. So now we can use this to get kind of a lower bound on the shape. So really, all you need to do is just find what M is, sort of the maximum quadrilateral that you can just place inside the moment image. Right, so for example, right, so it's some examples of this. Right, it's actually, I worked these out a few years ago now with optioning. Okay, right, so let's do the shape of a ball. Good. Well, so you get that, well, it's supposed to sit above the diagonal, so R equals S. We have the moment image of the ball. Let's go something like that. See. So this stuff is all in the shape. Then, right. So then, what is M? So now we have to put a quadrilateral inside the ball. Right. So the slope of the right-hand edge of the quadrilateral is that has slope -2. This has slope 1, so it's going to hit somewhere like here. So this would be M here. So this would be 2M. Right. So if I want this to sit inside C, the optimal solution, you're going to want M to be C over 3. Then this point sits inside the triangle. So, all right. So in other words, right, so if M is C over 3, you get this C over 3 here. You get this strip is included as well. Oh, sorry, that's it. So that's what you get. All right. So this lemma implies that this is a subset of the shape. Then we're kind of proving that this is actually equal to the shape. So this is exactly these are exactly the Lagrangian tori you get. Okay, you can do some others.
shape is always unbounded.
Yes. Right. Yeah. Exactly right, because of this lemma. Right. Yeah. Right. Yeah, unbounded in the y direction. So what else? All right, the polydisk case, right, the shape of a polydisk. Right, so remember, I'm always assuming A is less than B, otherwise I have to like reverse the factors a bit. Right. So what do you get here? So you have the moment image is that. Then you draw the diagonal. Right, then what's the maximum M here? Well, right, so now if you're going to put this quadrilateral in, it would hit the boundary exactly at A. So the maximum size of the quadrilateral is going to be A over 2. So we draw a vertical line at A over 2, and that's it. So that's the. And so this is above the diagonal, right? So that's the shape of a polydisk. So I'm going to stop computing these things. Right. So now what I want to talk about. Let's wait a minute. Theorem. All right. So now, so what about the ellipsoid case? So the shape of an ellipsoid. So now. So again, A is less than B. So let's do this. So then you draw. Oh, okay. Right, draw the diagonal. Okay, right. Actually, I don't know the answer to this. Right, so we need. I need an aside. So let's assume. Right. I'm always assuming A is less than B, but I also need to assume that B is at least 2A. So in other words, this slope has to be, we'll talk about the other cases. I want this slope to be quite steep, bigger than 2. Okay, so the benefit of that is this slope is steeper than 2 if you put the slope on the quadrilateral is 2 exactly. So the quadrilateral is going to hit it exactly at that point. And the quadrilateral will go here. And the maximum size quadrilateral you're going to get is going to be A over 2 still. And then you draw A over 2 here, draw up. And then that's the shape. Right, so that's it. Right, so I'm claiming. So this is the shape of an ellipsoid. So this is not so easy. Okay, so I want to say some things about that. Right, so we have two. Right, okay. Maybe we'll come back to this, but right. So there's sort of two approaches to this.
Can you read off of the shape, for example, the ECH capacities?
No, how you, well. Right, yeah, I think, right. No, I don't believe it, no. There's examples where the ECH is, yeah, we'll come back to that, but sort of ECH can detect. Well, ECH can obstruct embeddings that these can't. So like for thin ellipsoids, somehow these don't have enough information. But yeah, I don't talk about that. But sometimes, okay, but sometimes I claim these things do see more than ECH in certain cases. So it's, yeah, it's a bit. Right, okay, right. So this, all right, so in one of this theorem, so there's two approaches to this. So actually, right, so I proved this with Zhang, right? So it's a theorem from a few years ago. Zhang. Right, so this is the case when, right, so I still want B over A to be bigger than 2, but now I want it to be an integer. Right. So, well, okay. Well, and this is sort of a symplectic field theory style proof. So we're kind of, right, so we have some sort of ellipsoid here. Very rough picture, anyway. Right, this is the boundary of the ellipsoid. Maybe you have some L, which is the image of a product Lagrangian torus. So we have some kind of scenario like that. And the idea is to sort of find some sort of finite energy holomorphic curve with positive asymptotics on the boundary of the ellipsoid and one negative end on the torus. And then you can kind of play off the action of the positive ends, which depends on the parameters of the ellipsoid, against kind of the area class of the torus. So somehow constructing holomorphic curves can be used to obstruct Lagrangian embeddings, and turns out you can get sharp bounds in the case where B over A is an integer. But we couldn't get this to work for general B over A. It's not going to be nice to work, but not yet. But okay, so then there's another thing to try here. Right, so you could also try to reduce this to a sort of Lagrangian intersection problem. Okay, well, so second method. Well, right, so okay, so there's a theorem. Well, there's not enough, but right, there's a theorem with Kerman about Lagrangian intersections. So it's so just as kind of a warm-up, right? So it's right, so suppose L is a Lagrangian torus, maybe sitting inside a polydisk, or if you like, it's also true S2 times S2. Right, and I want to assume it has, tell you what this means, integral area class. So in other words, if you take any surface with boundary on L, integrate the symplectic form, you get an integer. Assume that. Okay, so then L has to intersect L11. So right, so L11 is a subset of P22. Right, so in other words, right, so if you draw P22, it's just the square. Right? L11 is, well, this is the moment, that's the moment image of a square. The moment image of L11 is just right, just the center of the square. Then, right, then the claim is that any integral Lagrangian torus in there has to intersect this product torus. Right, okay. But then if you draw the diagonal, the anti-diagonal here, this part of the thing is this is a ball, or the pre-image of this. So I think my notation, this is little b2. So right, so what's so this somehow gives you restrictions on which Lagrangian tori sit inside a ball. So it's a weaker statement, but a corollary of this is that 1,1, for instance, is not in the shape of the 2. Because if it was, what's this saying? This is saying that there'd be an integral Lagrangian torus in the ball, but if there was an integral Lagrangian torus in the ball, by this theorem, it would have to intersect the product torus, and that would be a contradiction. So this, okay, well, so 2, 21, 2. Oh no, because I got so right. So this is not actually big news, right? This is actually known a while ago, right? So there's calculations sort of related to what you said. So there's a lot of calculations of sort of the maximum size of a monotone Lagrangian inside a ball. So this was known in the paper of Chilibak, Monka. I think around 2015 they proved this. Okay, right. So so that's fine, but right. Okay, right. But what about the proof? Right, but the proof of this. Well, I guess the novelty is that there's no assumption on. So it's like a Lagrangian intersection result. So there's like a lot of that kind of stuff. But so the novelty here is that there's no assumption on the Hamiltonian isotopy class of L. Right, so the novelty is that there's no assumption on the Hamiltonian isotopy class L. Right. So okay, right. So in other words, so we couldn't extract this from flow homology. So somehow, so we're relying on dimension 4 and trying to work out how the Lagrangian sits relative to foliations by holomorphic curves. So we want to study. So I want to study L relative. So P22 sits inside S2 times S2. This has two foliations by holomorphic spheres in the two classes. And the question is to work out, somehow start stretching those foliations along L and say something about its position. So relative to foliations by holomorphic curves, holomorphic spheres. Right. Okay. So, well, anyway, right. So that's, you can try and do that. Right. But then, what I'm saying is that argument, it doesn't rely on Hamiltonian isotopy class. It turns out it doesn't rely on monotonicity that much either. And so it's, so, maybe, right. So it's, well, I'll come back to this at this time, right? But you can also try to work this argument in more general cases. So I also want to apply, if we're interested in maybe some E1x sitting inside a P1x. That's the ellipsoid. Right, so then, so now I'm saying, okay, an image. So suppose there's some Lagrangian torus inside there. Does it have to intersect one of some Lagrangian torus with the same area class outside? Right, so like maybe RS is somewhere there, maybe SR, like other examples. Right, so, so somehow, so that's the plan. So somehow this argument somehow it's relying all on foliations by holomorphic curves. The kind of things you can do, based on quantitative estimates, we can kind of drop the Hamiltonian isotopy condition and also monotonicity as well. So this is so this is It's a lot harder to prove than the other ones, but somehow that's Well, we'll come back to this if we have time, but I want to do some applications with this. So that's the main.
In all these pictures on the R equals S line, you're bounded. Is that always true?
Yes, that's true. Right, yeah. That follows from Chili back and Monk.
Oh, okay.
But maybe even further back it's bounded. Right. Yeah, right, yeah. So that's bounded. As long as the domain is bounded.
Oh.
Right, yeah. Right. There. So for example, then. Well, of course, there is this condition, right? So it's somehow, when I'm looking at the Lagrangian torus, I have this assumption that I'm only interested in excluding Lagrangian torus when the first factor is somehow big enough. And the idea is to somehow substitute this as your monotonicity condition. Oh, by the way, right, so I was going to say, the gap, okay, that's shape calculation, right? So let's suppose, still not. So the gap would be nice to fill this in. So the gap is, right, as far as ellipsoids go, right, so so let's suppose, right, so suppose I'm interested in the shape. Right, so now it's right, so I know when X is 1, this thing is just a ball. I know what the shape is. When X is bigger than 2, it follows from this. So it's, right, so the question is, what do you get in between 1 and 2? So all I know is that it contains, okay, right, so what's the M here? Right, so the point is now that X is between, if X is between 1 and 2, this is shallower slope than 2. So if you draw the quadrilateral in, try to do that, right? The quadrilateral has slope 2, it's going to hit at this point, M. Sorry, M2Ms. So the maximum quadrilateral is going to be, the M value is going to be less than less than a half. Anyway, so what you get out of this, you get the moment image, right? So you get the E1x plus I guess right, and then right, the width of the bar turns out to be x over x plus 2. But I only know that this is a subset of the shape. I don't know if that's shown. So for example, right, so so that's just checking how big n has to be to get this to sit inside the triangle. But okay, so it's a bit frustrating, but I don't know if that's okay. Right, but that's the bound we get. All right. What? So then. Okay, so for example, another definition here, but the definition. So x, some toric thing. This is not convex in the usual sense, right? We're going to call it convex. Omega is the region. Concave function. Concave. Right, so concave function looks something like that. Right? So this is what we call a convex toric domain. Okay. Right. Okay. So now, right. So this is a example of the last thing. All right. So okay. So we're going to choose some concave function. Right. So suppose you have one of those. Right. So f, maybe from 0a to infinity. Right. So this is going to be concave. So the second derivative is wanting to be negative. Right? And then I also want to assume, because of this b over a condition in the shape calculation, right? So I also want to assume that the derivative is less than or equal to -2. Then when you get to the right, so maybe f of a is 0. Good. So then, that's what this look like. So a is here. A bit more space. Right. So we're looking at some fairly move this in. Right, so looking at some fairly steep concave functions or something like that. Right, so this could be the omega. Right. Okay, so what's the shape of this? Right, so so what's the shape? So I'm interested in the shape, right, of x omega. Right, omega is just the area under the graph. So omega. Okay. Well, all right. Well, so right. So just so I have the argument from before. For sure, omega is contained in the shape. Then you can look at the maximum width of a strip going up the y-axis. To get that, you have to embed one of these quadrilaterals. But because this slope is bigger than 2, the optimal quadrilateral is going to hit at this point. Right? So the width of the strip is going to be r less than a over 2. So that's a subset of the shape. So now draw that blue. So you got a over 2. So right, there's also the diagonals involved here. Right, so all of this stuff is contained in the shape. Okay, meanwhile, right, so what is omega? Right, so what is omega? But because this is convex, it's an intersection of ellipsoids. Right, so this is the shape of an intersection of ellipsoids. And the ellipsoids you take are just the kind of like supporting hyperplanes here. So you sort of draw these things on. Draw these things. Right, so you take a union of all those. Right, so it's, right, so here's right, so EAB is going to be tangent, or the boundary of this is tangent. Right. Okay. Right. Okay. Right. Okay. But now, right. So because of this assumption on the slope, all of these things have a ratio at least 2. So I know what the shape of these things is. So this is contained in the intersection over all those ABs. The shape of this, which is exactly EAB plus union R, well, whatever it's going to be, right? R less than that. Fortunately, I'm using the same letter for different things. So let's say it's, maybe let's call these PQ or something. Right, so I've got, okay. Right, PQ. Yeah, I've decided on A as being the point. Okay. Right, so then, right, P over 2. Okay, so that's an upper bound on the shape, and it turns out there's not like a huge difference between these two things. So let's we do this, we say this is yellow. Well, for sure it's bigger than this stuff, right? But it turns out, fortunately, it's not exactly the same. But if you draw the tangent line at A, right, and then draw it up, eventually it's going to hit this strip at some point. So there's a point there. Label this, right? So it's right. So then there's what? Right. So this is what you get if you take the tangent line at the end point, draw it up until it hits the strip. That's a point. Right. Then there's another point which is strictly between. Right. So that's label. Right. There's going to be a right. So where the moment image hits the diagonal, we'll say that's DD. This is A over 2. So there's a point here somewhere. Let's call this E. So there's a point which is between A, or it's strictly between A over 2 and D, and that's the point where if you draw the tangent line at the point E, it's going to hit at 2E. So there is a unique point with this property. So it's not A over 2, for instance, because if you hit A over 2, if you draw the tangent line at A over 2, for sure you're going to hit past A, so you're not satisfying that. On the other hand, if you draw the tangent line at the diagonal, because the slope is bigger than 2, it's going to hit the x-axis before the y. It's going to hit the x-axis before the x coordinate increases by d. So it's somewhere strictly between these two points. And then you've got to like round the blue stuff. So you've got to, that's a tangent line, right? So I've got to like round it off and do that. So I'm making this theorem look good by drawing this badly. So anyway. Okay, so that's, yeah. So the shape is between the yellow and the blue, right? And so there is this little gray area here. So that's the ambiguity. That's why I don't know about the shape. Otherwise, we have sort of a calculation for these things. All right. Okay. So now. All right, that's right. Okay. So then you can get embedding theorems, which I don't think you can get out of ECH or anything else. Right. Okay. All right. So corollary. Well, we just choose 2 functions now. All right. So FG, right. Same kind of thing. Infinity. So same thing. They're both concave. Right. So F double prime, G double prime. Negative. F prime, G prime less than -2. Right. Okay. Right. So I want, right. So let's assume somehow the point is between E and A, the shape is actually seeing the moment image. And so that's kind of the thing. So the moment image is actually an embedding obstruction on this little interval. Right. So let's assume that f of x equals g of x for all x, right, outside of that interval. So E, D. All right. So at least like so that they're going to differ somewhere on this interval. Right, so then, so then the toric domain associated to f, right? So this means just the area, the region under the graph of f, embeds into xg, if and only if f is less than g. I'm a little bit of proof this, right? So any kind of perturbation. There's no symplectic embeddings unless you strictly move it inside. Right. But I do need this assumption, right? So somehow, if you start messing around with that outside of that interval, then it's somehow not detected by the shape, so I don't get obstructions. Right. Okay, right. So that's somehow what this stuff sees. How long do I have?
Well, at least 10 minutes. I don't
10
remember
minutes.
exactly when we started.
All right, okay, let's say 10. Okay. Any questions about this? So that's okay. So that's what this stuff sees, right? So it's which I think is somehow invisible to other. I mean, a lot of other capacities kind of focus in on the diagonal, and somehow this sees a little bit more somehow. All right. So okay. So that's right. So that's where this stuff is good. So I just wanted to mention. Talk a little bit about right where things aren't so great with this. Okay. Well, right. Okay. Right. So the shape is certainly not, in general, a complete obstruction. So, for example, okay, this thing, if you take an ellipsoid, this is automatically contained in the shape of a ball whenever C is bigger than 3. So this sort of thing, it's way out. So if you just draw this, and maybe I draw a ball of size 3, then what's the shape of this? Right. So remember, for the ball, the strip has width a third. So you draw the line up at 1 here. But E1x, it's like its maximum R coordinate is 1 anyway. So E1x is completely inside the shape. So I get no obstructions to this kind of thing. However, C bigger than 3 is certainly not necessary to get an embedding of an ellipsoid into a ball. So, out. Yeah. Okay. Well, right. What am I saying? Right. So, sorry. Right. So I mean, 3 is not sufficient to get an embedding here, right? But C bigger than 3 is not sufficient. Right. So, for example, by thinking about volume. Sorry, I could put x equals 1,000,000 there, and there's no symplectic embedding because the volumes don't match. Okay, so so I have this. We decided to try and extract more information from the shape, right? But if we're given a symplectic embedding, so for sure the shape of x is contained in the shape of y, right? Just because every Lagrangian in here can be mapped into here. But in fact, if it's coming from a symplectic embedding, you actually get a continuous family of Lagrangians sitting inside here. Right? So there is some topology which potentially could give better obstructions. Right? But in fact, there exists a continuous family HRS of Hamiltonians. Right? These are all Hamiltonian embeddings, of course, so Hamiltonians. With, if you take the corresponding Hamiltonian diffeomorphism and apply it to LRS, then that is going to be contained in Y for all RS. Actually, I'm talking about Toric, at least for all RS contained in the moment image of X. Be its omega. Okay, so, right, if this happened to be Toric, the omega. Well, which is somehow more information than just saying that the shape of this is contained in the shape of this. So, okay, so let's, right, so if this is true, all right, so let's write this X, Y, right, so I put a little L here. So this means I can get a continuous family of Lagrangian embeddings from all Lagrangians contained inside the moment image. It doesn't imply you get continuous family for all Lagrangians contained inside the shape. But anyway, so we get that. And it turns out, okay, so we have L. Oh, L is just a notation. This just means a continue. This means I can embed the family of Lagrangians continuously. So, so this is potentially a stronger obstruction. So X. So symplectic embedding implies. Okay, right. So, right, but it turns out we can also get obstructions to this. Right, so we can also, right, so we can get obstructions to, right, by similar sort of SFT methods. Under, okay, right, so it turns out not all the time, but under, so this is somehow related to Lagrangian knots, right? So under an unnottedness, sorry what that is, an unnottedness assumption. So this is Zhang. Right. So it makes this story better. This, okay. Right, so this works when X is an ellipsoid. Right, it makes this sound better. So Y can be a ball, an ellipsoid, or a polydisk. This all works. So maybe I just write down the statement for the ball, but this sort of, you just tweak the numbers a bit and it works in these other cases. Okay, that's what we have here. Right, so E1X. Okay, let's just say that there exists a family of Lagrangian embeddings, E1X, L, B, C. Right, but I need an unnottedness assumption. So with and here the unnottedness assumption applies to the Lagrangian on the diagonal. Right, it's 1x. This point here is x over x plus 1, x over x plus 1. Okay, so there exists a Lagrangian embedding with, okay, if you look at the image of L, x over x plus 1, x over x plus 1, I want this to be unknotted, right? So in other words, it's Hamiltonian isotopic to the inclusion. Lost that one. Right, to the inclusion, right? X over x plus 1. Inside the ball. I mean, for sure, it's isotopic to this inside C2, but I want the isotopic to have support inside the ball. So this, okay, that's right. So I'm getting obstructions with this kind of extra hypothesis here. If and only if C has to be bigger than 3x over x. Okay. So it's that. All right. So then, okay, well, right. So that unnottedness assumption is kind of stopping me obstructing symplectic embeddings. But right, but it turns out it turns out the unknottedness assumption is necessary. Otherwise, this is false. Right, so it's false. In other words, I don't get this bound without the unknottedness assumption. So this is false without without the unknotted.
Do you mean you cannot improve the bound from the discrete version? Or
No, it's still a better bound.
it's still a better bound?
Right, but it's not good enough.
Okay.
It's right, it still doesn't well, I mean, this is not right. So the L embeddings obstruct symplectic embeddings, but this is an L embedding with an extra condition, which doesn't necessarily obstruct. It doesn't necessarily obstruct symplectic embeddings, and in fact, it doesn't. So for sure. Right, so in fact, okay, right, in fact, right, so what I'm saying, so there's a famous paper of McDuff and Schlenk. Right, so they worked out. Right, they know what this function is. That's fine. So this is the inf of the set of C such that you. And it turns out it's possible, right? So sometimes f of x is less than 3x of x. So maybe don't get the story here. In fact, you can even tell you about, in fact, almost just sort of graph this thing. Right, so if you want to graph, okay. I'm always writing the factors in order, so I might as well assume x is bigger than 1. So it's I'll center it here. These are 4-dimensional embeddings, so volume is a lower bound. So we try and draw square root. So square root, something like that. That's y equals square root of x. Okay, then there's another interesting graph. Right, this 3x over x plus 1, which goes something like that. This number here, this is tau to the 4. This is all due to McDuff-Schlenk. So this f of x square root is a lower bound. It turns out what it does, you keep like bouncing between these two graphs. Right, so you go horizontal, diagonal. The diagonal line goes through the origin. So that's what they worked out. In fact, we even know what these numbers are. I think this is called B0. Right, where it hits the 3x over x plus 1, B1, B2. Right, so Bn, it's Fn plus 2 over Fn. So these are the like the odd index Fibonacci numbers. Okay, so anyway, right, so certainly it's not always true that to get an embedding you have to be above 3x over x plus 1. In fact, so what does this mean? That means if this graph lies strictly below 3x over x plus 1, and then you look at the image of this Lagrangian torus, for sure it's a knot. Because if it wasn't a knot, then I would get an L embedding with this condition, and then C would have to be bigger than 3x over x plus 1. So when, okay, so in particular, right, so let's say when x is between b n minus 1 and bn, then you look at the embedding, and then you apply it to x over x plus 1, x over x plus 1 is a knot. So it's an embedded Lagrangian, but it's not Hamiltonian isotopic in the ball to the product Lagrangian. And in fact, there's a paper by Casals and Viana, I think the first one, so Casals, Viana about this. I mean, we know what this knot is. So there is no complete classification of monotone Lagrangian tori in the ball, but we know infinitely many, and they correspond to Markov triples. So anyway, I don't have time to talk about that. But anyway, it corresponds to they know what it is. Right, so there's a one-to-one, well, there's a correspondence between known Lagrangian tori and Markov triples. And anyway, and this one is, I think it's Fn minus 1 Fn. So that's, so anyway, so I'm getting kind of infinitely, it turns out these knots are all different. It turns out I'm getting infinitely many Lagrangian knots in these symplectic embeddings. Okay, and then what we can refine our theorem a bit. So now, yeah, right, so that's, all right, so, right, so the problem with this result is I've got this unknotted assumption. Now I'm saying I can weaken it. So let's just say, right, so let's say, find that. Right, so E1x goes into BC with, right, so L x over x plus 1, x over x plus 1, Hamiltonian isotopic. I'm not claiming it's an unknot, but I want to assume it's one of those LNs. Right, Ln, some n. Right, and, right, okay, so I'm weakening that assumption, but I have to stick another one on. And let's suppose that x is bigger than tau to the 4, equals tau to the 4, then all that still implies that c is bigger than 3x over n. Right, I think that's a punchline of all this. Right, okay, so this looks like it's related to stabilized embeddings. Right, so okay, so one more sentence, right, so stabilized embeddings. Right, so on the one hand, just the construction, I need Toric again. If you have a family of Lagrangian embeddings, that implies that you get a stabilized embedding. Right, so what is this? Right, so a family of Lagrangian embeddings, that means every Lagrangian inside X, I can find a continuous family of Hamiltonians, which are taking them in Y. They might all start intersecting, but if you add on the extra factor, you can kind of pull those intersections apart. So you get a stabilized embedding. So, okay, so we've got that. But then we have there's like a lot of calculations of stabilized embeddings, and every case where these are actually known, the bounds are exactly the same as we're getting for the Lagrangian embeddings. Right, so I think it's true to say it's sort of in many calculations, maybe in all calculations, right, in many calculations, this is not completely solved, right? Right, so the bounds for this exactly match. So it looks like this might be an if and only if is what I'm saying. Right, so exactly match X, L. In particular, right, there's a conjecture. So she conjectured E1x BC when right, so assuming x is bigger than tau to the 4 implies c is bigger than 3x over x plus 1. Okay. And that's okay. Well, so it's not just coming out of the blue. So that's there's a lot of evidence for that. There's infinitely many x values where this is being checked. So this is a theorem. Well, I mean, a lot of people, Christopher Gardner, could write some names here. Me, I guess, Kerman. So, maybe either Siegel, the most, right? So this conjecture is true. They can almost just give Kyler a number and he checks it. Right, so this is true for many, right, infinitely many cases. Okay. So right, and but then okay, to make this more convincing, this is the case for the ball. You get the same story if you stick an ellipsoid here or a polydisc here. We still get estimates on stabilized embeddings. They still match the Lagrangian embeddings. Right, so the conclusion is, at least if x is one of these many values, you can drop the unknottedness condition completely. So then, right, in those cases, we know exactly when you can get these Lagrangian embeddings. But unfortunately, we can't, doing this, we can't prove this conjecture because there's no like general argument that the stabilized embedding implies as a Lagrangian embedding. So that's kind of the gap. I mean, it'd be nice to say, okay, we've got bounds on this for all possible x. Could we get bounds on these for all possible x? But currently, that's a missing step at the minute. So anyway, so I'll sorry, time's out a little bit of that. Thanks.
Thank you. Questions?
So maybe with this, like when you study the case of polydisk or others, like not the ball. So, I mean, are there still like these things like ants, like the
Right, for the cube, we know a few of them. Right, yeah, in general, I sort of know that but I don't think it's the same classification in those cases. Right, yeah. Well, right, yeah, so there's a, right, yeah. So we know there's knots, and we know these conditions match. Right, you're right, but the knot theory is not as developed. It's best for the ball.
and you think that maybe or it's possible for toric that this actually Lagrangian embedding and stabilized embedding might be the same thing? Like
Well, right, I mean, it's the same in kind of all cases that I know. So right, so you get an implication in this direction, and every single calculation seems to match. So it looks very similar. Right, so I mean, it's very tempting to believe that. So.
I have a question. From the shape invariant, you can get a bound for like a lower bound for the displacement energy of your domain.
Right,
Because you know
yeah.
the displacement energies of these Lagrangians.
Right, exactly. Right. So in fact, yeah, so we know the displacement energy, because I'm always assuming R is less than S.
Yeah.
Yeah, right, so this is R.
So it's R, like the maximal R that is, so like the maximal R that is contained in your shape will be bounding your displacement energy. So one question is, do you think there are examples in which it would not be equal? Like it sounds like maybe for toric domains, it should be always.
Yeah, so this, right, yeah, so these sort of so this tends to be the point on the diagonal.
Yeah.
So then you're saying, is that
okay,
always,
maybe.
is that always the displacement? What about the ball? I think for the ball already this fails, right? Right, so for the, right, so if you look at the ball, right, so it hits the diagonal at C over 2.
Yeah.
Right, but the displacement energy of the ball is C, I think.
Wait. It hits the diagonal.
Right, C. Right, so C over 2 is, well, okay. But it's, at least if I'm assuming R is less than S, the maximum R you're going to get is C over 2. Somehow less than that.
I see.
Yeah, there's some certain cases somehow this is very weak. Somehow this shape works well in some cases, but other cases it fails badly in some cases. So I guess that's one of them. Gromov's non-squeezing, actually, I can't prove that either. I think I'm off by 2 for something like Gromov's non-squeezing, for kind of the same reason.
Oh. Yeah, that's weird.
So I can only prove that a ball embeds in a cylinder. I can only obstruct that if the capacity of the ball is twice the capacity of the cylinder. It's kind of, right, yes, yeah, maybe that would have been a better example than right, yeah. So this is not like the answer to everything.
So is the goal more or less to get a complete abstraction for toric domains?
Wait, complete what for toric domains?
Like a complete abstraction to embeddings of toric domains.
Right, well, yeah, for sure.
Is that?
I mean, I think like a general goal.
Do you think it's an achievable goal, or is that?
Well, it's already known for like Right, for like embedding concave domains into convex, ECH already gives some kind of, I mean, at least we know ECH is like a complete set of obstructions. So yeah, I mean, right, it would be fantastic. Right, yeah, I mean, to me, that's a basic problem, like even understanding, like say, convex embeddings into a ball even is an open question. Right, yeah, right, yes, it's a fundamental question. Yeah, okay, I mean, this is some information, but it's probably not like the complete answer. Yeah, this embedding question, yeah, I mean, yeah, there's a lot of work, but it's still open for toric domains, even, you know, even convex toric domains. Even polydiscs into a ball is a famous one. That's an open question. When PAB embeds into BC, it's open. And PAB, this is just too simple. It just doesn't give enough. Okay, maybe this answers the stabilized question, but like something like polydisc into ball. But it's a long way short of getting just the 4-dimensional embedding.
I mean, I'm not sure if this makes sense, but like, is it? I mean, this Chekhov torus are very unexplicit to kind of study like shape type thing starting from them, or?
No, I mean, they're not so bad. You could sort of probably build them in. It's just more notation. That's kind of, I mean, I kind of know, like for these domains, I sort of know the maximum scale you can put on the Chekhov torus. It just, I mean, as far as these estimates, it just works the same as just the monotone ones. So as far as these embeddings, it seems you can embed it if and only if you, well, probably not true in general, but for these kind of domains, it seems you can embed it if and only if you can embed that one.
And
So
I guess
maybe it's, yeah.
Implicitly, I was interested whether these embedding questions do see difference between, like, you know, as Lagrangian submanifolds, they are different, or.
Oh, right. Oh, right. So could I somehow? All right. Yeah, because potentially. I mean, in a sense, it's sort of trying to, right, if you go to this, for this kind of, maybe that's what we're sort of trying to get at here, right? That somehow these continuous families are sort of seeing where these Lagrangians are going. So, yeah, so yes, I guess I don't know, but potentially you're right, yeah. It's the shape itself, it doesn't seem to care much, but you get in these knottedness questions, so.
Thank you.
Let's thank Richard again.